Hello everybody to our today's tutorial. I'm Michael Kaiser, Director of Product Management Kathrein Solutions, and today I have a very interesting topic for you. How to select an UHF RFID antenna. So let's start. You can see we have a lot of different applications for UHF RFID. And for each application, we have certain requirements. We have for logistics, for manufacturing, for transportation. This means for identification of vehicles, for the healthcare business, hospitality, but also for access control. And in this case, all the antennas will be used and has to be selected in the right way. With this next slides, I will give you some hints how to select this. If you have interested in this application, have a look to this document you find on the bottom, IoT Portfolio 2024. To give you already a first hint, you can also select our flyer for logistics and production. And there you can find a lot of different applications based on logistics and production. So typical doctor solution, supply chain, but also Kanban systems and so on. And here we show you also some detailed information, like here the doctor overhead solution, but doctor gate solution, and also an information how which antenna, which hardware is selected. In general, we can do the selection of the antenna in two ways, in two possible orientations. One thing is to take the largest possible read zone and select this transponder later on in the software. This means you have a big antenna with a big read range, with a big area to cover, and then select the software transponders. The second point is to have a very selective antenna with a very small and defined read zone and read only certain transponders. And how to select these antennas and how to define these antennas, you will find here with our radiation pattern sheet, which you will find on our homepage. With each product, with each antenna, you see this comparison list where we have different parameters and also a kind of shape of these antennas to give you an idea how the antennas could look like, how the antenna could work. The most important parameters of these antennas is, of course, the antenna gain, but here we'll see we have different parameters in dBi, dBic, dBd, and I will guide you through this channel and give you some ideas how to select the right one. We will talk about the opening angles. This means the half power beam width. This means how many energy will be focused in which area, in which room. We have symmetrical beams, we have asymmetrical beams, and I will guide you through this. Also, a very important parameter is the polarization. This means in which orientation the tag will be received. There are some linear antenna possible, where the antenna alignment and the transponder alignment has to be suitable. And we have circular antennas, where it doesn't matter in which orientation the tag is aligned in the field. We'll have some requirements for the read distance, and you will see that one and the same antenna can be focused or broadband. It depends on the distance of reading. And we'll have some words about indoor and outdoor usage of the antennas. So let's start. That's the most important parameter of the antennas is the antenna gain. What does it mean, antenna gain? So we have a typical scenario. We have the UHF RFID reader. We have an antenna. And this antenna builds up a field, an electromagnetic field. And as soon as the transponder arrives, this field comes in the field, it will be activated and will be backscattering the signal. And this signal will be received from the antenna again and brought to the reader to read out the data. So let's start with an first antenna. This is a theoretical antenna. This is an isotropic spherical radiator. This means the field will be built up in a ball around this antenna. When we feed in a power of 1.256 watt in this antenna, we have in a distance of 10 meters and power density of 1 milliwatt per square meters. This means in an area of 1 by 1 meter, the energy is 1 milliwatt and the tag will be activated by 1 milliwatt. And all over the globe, all over the ball, we have the same energy. When we select a dipole, And by the way, all transponders are dipole antennas. We have this behavior. And to give you an idea how it looks like a donut, not a ball, like a donut. And you can imagine on the position where the antennas are, we can press in with the fingers, and though we have less power, and in the direction where we transmit the signal, we have more power. So it looks like a donut. You can imagine when you have a transponder and there's a donut around. In this direction, I have high power. In the direction 90 degrees left and right, we have less power or low power. So in this case, we do the same. We feed in 1.256 watt, and in 10-meter distance, we have more power. So be careful, it's not more power in total, so we don't generate energy. The point is we focus the energy in this direction. You can imagine we have the spherical isotropic radiator before as a ball, and now in this direction we have 0.64 milliwatt more. This means we focus in this direction, we focus the beam in this direction. The same we do with standard antennas. If we have a standard antenna like this 30 and 70 degree wide range antenna from our Bro line, we have 11.5 dBIC, and this gives you a power density in 10 meters of 4.3 watt. 3 watt milliwatt per square meters. So again, an increasing, and you can see here with the radiation pattern that we are focused in this area. Do we have a comparison with an isotropic spherical radiator where we have all the energy is the same in the complete 360 degrees? We have in the main direction more power. And here you see we have 6.3 dB more. 3 dB is doubled, so double and double means 4 times, and that's why we have an increasing from 1 milliwatt per square meter to 4.3 milliwatt per square meter with an antenna of 11.5 dBIC. Again, compared with this dBi, dBd, dBIC, we have from 1 milliwatt to 1.64 milliwatt to 4.3 milliwatts per square meters. And here you see the different antenna we have, and you know now dBi is a compensation value. We compare the antenna gain always with an existing dipole antenna or with a theoretical isotropic antenna. If it's an I end, then you know it's based on the isotropic antenna. So dBi is a logarithmic increasement of the transmitted power in relation of an isotropic spherical radiator. dBd is based on the dipole radiator, and dBi and dBd are always linear gains. And here we come to explanation of the polarization. So you see on the left a linear vertical polarized antenna, and on the right a circular polarized antenna. And you see this antenna field will build up that we have only in the horizontal level. This means the transponder has to be also aligned in this direction. Then we have a good reception and we can activate the transponder. In the linear polarized antenna, we see that the effector, the pointer is rotating, and this means it doesn't matter in which position the tag is aligned, we will find some position where we have a good alignment between the antennas and the transponder and a good reception point. Well, it means that we have to split the energy in 2 planes with a circular antenna. Yeah? This gives you the benefit that we don't care about the position of the transponder, the alignment of the transponder, but we have to split up this energy. And also the response of the signal has to be bypassed to this splitter. And this means we have a loss of 3 dB. That's why we are talking about polarization loss. With the circular antenna, we have 3 dB polarization loss. And this means if we have really a weak scenario where we have weak transponders and weak reception signals, then a linear could help. But keep in mind, then you have to take care about the alignment. The antenna has to be aligned in a perfect way. So this is very often done, for example, for vehicle identification, when you have fast traveling cars, when you have big distance, about 20 meters, then you have to take care that the transponders are always aligned in the same positions. This means the position of the tag in the windshield or the position in the headlamp tags should be always the same, structured in a good way. Otherwise, you will lose this transponder. If it's mounted in a different way, you can't read it. Yeah? But on the other side, you will have this 3 dB polarization loss. You don't have this 3 dB polarization loss, and you have the 3 dB higher signal from the back signal from the transponder to the reader. With the circular antennas, we have this 3 dB loss. In the forward pass, we can increase the power, of course, to overcome this 3 dB, but the backward pass can reduce or will reduce the power by 3 dB, by half. But in this case, for a logistics application, 1 meter, 3 meter, 5 meters, 10 meters. In this case, the alignment of the antenna is more important. That's why in this case, we would recommend to take a circular antenna. So you have seen we can convert this dBi to dBiC, where we have this 11.5 dBiC, which we have with our standard 30 by 70 degree antenna. And this means 8.5 dBi because we reduce by 3 dB. We split the energy in both halves. So dBi to dBiC is a difference of 3 dB. So as we already said, if you have a higher antenna with a higher gain, the less energy you have to feed in. The less energy the reader has to supply. The higher antenna results in a greater read range with the same input power. Note, take care, we have a maximum allowed power in Europe of 2 watt ERP, effective radiated power. And the higher antenna gain, the smaller reflected signals can be with the same input power. So greater distance, smaller transponder signals, weak transponder signals, and focus reading. In this case, we recommend higher gains. We have talked about this standardization of 2 watt ERP and about the half power beamwidth. We will have the next slides. So you see on the left side the 30 degree antenna focusing in the main direction, and I have a half power beamwidth of 30 degree. On the right side, you see the 70 degree antenna. Both are standardized for the maximum allowed power of 2 watt ERP. This means 33 dBm ERP. And with the left antenna, with the high gain antenna of 11.5 dBiC, it's enough to have an input power of 26.65 dBm to reach this 2 watt ERP, this 33 dBm. With the right antenna, we have increased the power a little bit to 29.65 dBm. We have this full power. This means when we are in the main direction, the tags will be aligned with the same power. We have the same read range. We have the same input, but left and right, we have more power. To feed this power in, of course, we need a little bit more, a little higher input power to focus this beam in this shape. Half power beamwidth means that we have a drop of the power by half. So in the main direction, we have the full power standardized, for example, to 2 watt ERP, and left and right, when the power drops by half, this means by 3 dB, we have a certain angle, plus 35 degree, minus 35 degree, and this gives you an aperture angle of 7 degree in this case. And of course, with the 30 by 70 degree antenna, we have this focusing in 15 degrees because in 30 degrees because we have left and right 15 degrees, which gives you the total sum of 30 degrees opening angle. And on the left side, you see the 70 degree. As we said, the higher half power beamwidth angle gives you more energy over a larger area. If you have to read not only in a spot, if you want to read a broader side, you can use although this broader angle to activate the text, to read the text. This angle is not a stop of the reading. This is only half power beamwidth. This means also above this angle, you can read transponders outside of this angle. And when you have such an asymmetrical field, which we have with a 30 by 70 degree antenna, then the smaller angle is with a longer side of the antenna. Here we are focusing, and here we have this smaller 30 degree antenna. You can also compare here, plus minus 15 degrees gives you 30 degree, and on the right side, we have plus minus 35 degrees. When we have a kind of application, and we have this focusing read zone in a distance bigger than 1 meter, so 2 meters, 3 meter, 5 meter. Then you see on the left we are focusing and we read only the transponder in the middle. On the right zone, when we have a wider reading area, we can catch more tags in this range on the left and the right because we have a bigger angle of 7 degrees. The same we have when we have a lower read range, read distance. This means are we away from the antenna 1 meter and more, then we have on the left side a narrow beam and on the right side a wide beam. And be careful because when you are closer to the antenna, for example 0.3 meter or closer, then the dimension of the antenna is important. This means in this area we have with a 30-degree antenna a wider beam and wider detection area than with the 70-degree antenna because the dimensions, the size of the antenna is smaller. So you see, it's very important to know also the reading distance. Far away, this means 1 meter and more from the antenna, then we can trust, we can rely on the half power beam width. Are we closer than 1 meter, typical half meter or 30 centimeters, then the physical dimension of the antenna is important. Finally, some words about the usage indoor and outdoor. With the Pro line of the Kathrein antennas, you will find the antenna will have an IP protection class of 67. This means they are useful for outdoors. The 6 stands for completely dust tight, so no dust and no water comes in. And 7 means also we have no water ingress, even we submerge the antenna below water. With the IP54, and this is a typical for our edgeline antenna, which is coming soon. We have still outdoor behavior, but with an IP protection class 54. Yeah, so this means dust can be come in the antenna, but we will have no damaging of the antenna. And splashing water from all sides is allowed. So typical scenario on a dock door, when the door is closed, you have no rain, no snow, but sometimes when the truck arrives, you open the door and some water, some rain, some snow comes in. This is no problem for such antenna. And we have typical indoor antenna, like this smart shelf antennas, where we have a dimension of a bigger 1 millimeter can come inside of the antenna, but have no harmful behavior with this. And of course, no water is allowed in this application. Yeah. In some case, an outdoor antenna is also useful indoors if you have really heavy mud and dust inside, or oil, or some water, or some waste inside of the application, or if you are in a heavy-duty application, for example, on lorries, on trucks, on forklifts, then it could be useful to have also an outdoor antenna. I forgot one thing for the outdoor antennas, of course. For all our antennas, we will have a vent element, a so-called GORE element. This means we have a small element which allows the unit to breathe. So you know when you have a change from hot to cold and cold to hot, and you have a very closed housing, then it could be possible that the gasket is always bending. So, for example, you have a hot antenna, then a rain shower arrives, it cools down dramatically, and the difference of the air pressure inside and outside will bend this gasket permanently. When we have now this core element, which we have for all our antennas for the Pro line, for the most of the antennas of the Pro line, then we have not this problem with the bending of the gasket, because the air inside, the hot air can breathe, can go out, and inside depends on the different air pressure. With the smaller size of the antenna, as you see the smart shelf antenna and the low range antenna, we don't need this core element because the volume is too small, and these antennas are also supersonic soldered, that we don't have this problem with these antennas. They are IP67 also without this core element. The bigger sizes with a 70-degree antenna, with a 30-degree antenna, we have this vent element included. Finally, the summary of this lesson. So we have seen that we have different application we can use with this antenna parameters. The antenna indicates how signal is transmitted in the main propagation of the antenna, so this means the main direction of the reading. The antennas with high gain are selected for weak transponders or for long distances. Keep in mind with the 3 dB polarization loss, if we have such an application where really this weak signal is very important to catch, maybe a linear antenna could be helpful, as I said, for example, with a long-range reading of a vehicle identification on a tolling station where we have to catch cars in a distance of 20 meters, and the cars will arrive always in the same direction, and the alignment of the transponders are always the same. Okay, we have talked about the aperture angle of the antennas. Higher angles gives you a wider range of reading. So if you have to focus on the transponder, if you want to read only a certain transponder, then maybe you have to use a focused antenna. If you want to catch a bigger area, you can use an antenna with a bigger half-power beam width. And very important, the reading distance. This means all these parameters we have shown about the gain, about the half-power beam width, gives you an indication for the radiation bigger than 1 meter. If you are closer than 1 meter, the geometrical shape of the antenna is important, and you have to take care. And of course, indoor and outdoor has to be also taken in account for your application. Have a look. Also, if you have an indoor application and you have dust or water or oil or something like this, maybe an outdoor antenna can be also helpful to run an indoor application. So many thanks for your attention. I hope you have seen and learned something which is important for you and is necessary for you. If you have questions about this lesson, and if you have questions about the antennas, please let me know. Many thanks.